Okay, well, this is an intimate crowd, and this is obviously the dedicated crowd, so we appreciate that. So why don't we get started, since we probably came here to learn some 61C as opposed to socialize. I don't know. I guess we could socialize. Okay, so I'm not going to, no, I'm going to try to get out of here. So the news item, don't spend too much time on it. I basically did a search of network and Turkey, and this was the first article that came up that wasn't about networking in the country Turkey. So I put it up, but it is actually kind of interesting. Deploying network infrastructure is expensive. There's not many companies who can do it, and now they're trying to all merge. And when they merge, competition goes down. So if AT&T and T-Mobile are able to merge, I thought this is interesting. They would have more than 130 million subscribers, which I thought was probably half or almost half of the U.S. phone-using population. But then Dan told me he has two phones, so maybe I was, but whatever. It's a big percentage. Okay, so that's that. So why did I care about networking in Turkey? Well, Turkey's part should be obvious, I hope. The networking part is because that's what we're going to talk about today. And so two things we want to do today. We want to finish discussing the whole issue of, remember when we talked about I.O., we said there were two ways. Well, when we talked about I.O., the challenge there is that the processor's super fast. The I.O. devices range over 7 or 8 orders of magnitude in how fast they are, but even the fastest ones, aren't necessarily as fast as the processor, and so there's a speed mismatch you have to do. Plus, a lot of the I.O. devices, they're external, right? So you don't really have control over when they do something. So think about a mouse or a keyboard or a network, which is what else we're going to talk about. So what I want to finish today is we talked about two ways of interacting with I.O. devices. Polling, right, where the CPU just goes in a loop where it checks a special ready bit, and it keeps looking until that ready bit is actually set to ready, and then it goes and does its I.O. And if you're reading from a disk, what you'd do is you'd do that a bunch of times. You'd get data in 16-byte chunks or something like that, and you just do it until you read the whole page. Okay, so that was polling, and the problem with polling is it's expensive, right? Because you're basically burning instructions that whole time. And so we looked and we said, okay, for a mouse, you probably want to sample. You want to check the mouse once every 30 times a second, right? And that'll be enough to sort of get a good picture of what's going on with the mouse. It'll probably be more than enough. And the cost of polling 30 times a second on a processor that can run 2 billion instructions or more a second is not really worth worrying about. But when we looked at things like polling for a hard disk, that started getting more expensive. And so the question is, how else could you interact with I.O. devices? And the answer is this idea of interrupts. And so what I want to talk about today is a little bit about how interrupts work, not in horrible detail, but just so that you see it. And then another type of I.O. device is the network, right? The network is basically how you do I.O. to the rest of the world. And so we'll talk very kind of high level about network. So my goal today was to sort of not tax your brains too much. You're showing a lot of dedication by not being on a plane to Hawaii or wherever you celebrate Thanksgiving. So, let's just go with there. Okay, so what's this idea of interrupts? Well, you don't actually have to you don't have to be thinking about I.O. just to worry about this idea of exceptions and interrupts. Because we've already seen a bunch of places where, even in our normal processing, unexpected things can happen. Okay, so what's an unexpected event? Well, an overflow, if you're doing an addition, an overflow is an expected event. A divide by zero is an unexpected event. Trying to access a part of memory that you're not allowed to access, right? That's an unexpected event. Trying to give the processor an opcode that isn't a real opcode, that's an unexpected event. So there's lots of things that happen, right? So we've built this really complicated pipeline system that's doing out-of-order execution. It's running 5 or more instructions at the same time. And it's just chugging along. And every once in a while, something weird happens, something that's going to mess up the pipeline happens. And so in general, those things are called exceptions. Exceptions arise, mostly within the CPU, right? So they're not external events. They're kind of things that happen while you're running your program. And then there's this other notion of interrupts, which is the same kind of thing, except it's from an external controller, like an I/O controller. So, when somebody presses that key on the keyboard, that's an external event. You got to be there to listen to it. So that's an interrupt. Okay, so different people use these terms differently, but we're going to follow the MIPS convention. So the MIPS convention is that exceptions are things that happen internal to the processor, right? And so they're synchronous. As you're running an instruction, it trips across a problem, and then you have to deal with it. And that problem might be a page fault or a cache miss or a TLB miss or an overflow or something. And then the other word we're going to use is interrupts. And interrupts are asynchronous. They come from the outside, and they're not related to the instructions that we're running. Okay? Or at least they're not directly related to the instructions that we're running. Okay. So how do we handle these things? So in the MIPS architecture, there's actually a separate. So we've been sort of telling you about the main processor. A lot of times there are these things called coprocessors, which are sort of very specialized processing units that handle certain things. And in MIPS, there is a processor that can handle certain exceptions. But we're going to sort of ignore that. We're going to assume that everything's happening in the main processor, which is the one that we've been studying. And basically, we'll do with exceptions first, which are the ones, right, that are caused by instructions that you're running. So what will happen when an exception happens is there's a special register, right? So we're going to add, whenever we extend the capabilities of our system, we tend to add new registers and control signals. So that's what we're going to do here. We're going to add a new register, which is the exception program counter. Okay, and that's going to be the program counter of the instruction that was running when the exception happened. Okay, so if you're doing an add and that add overflows, there'll be an exception generated, and it'll be that add instruction that was running at the time of the overflow. Okay, and in fact, it's that instruction that caused the overflow. So we're going to know what instruction was running when the exception happened, and there's another new register we'll add called the cause register, which is we've already talked about. There's a bunch of different exceptions, and so you want to know when you get an exception, you want to know which one you got, and there's two ways to do that. The way we're talking about here is when you get an exception, you automatically get moved, the PC gets changed to this special address, which is the address of an exception handler, okay? And that's code that's going to look and deal with that exception. The way we're talking about it, there's this cause register that what that handler will do is it'll look in that register, and in that register there'll be a code that says, hey, this is the exception that happened. So for simplicity, imagine there's only two exceptions we could handle. One is an undefined opcode and the other is overflow. Then what would happen is when an exception happened, you save the PC and the EPC, and then the control gets shifted to this address. When the address, the first thing that the instruction that address is going to do is look in the cause register, and if it sees a 0, it'll say, oh, okay, I just got an undefined opcode. Okay, what are you going to do when you get an undefined opcode? Probably crash, probably just throw your hands up and terminate the program, right, and report an error. And for overflow, probably the same thing. So, but you report a different error. Okay, so you can look in that cause register and it'll tell you, what happened. And usually they're going to be more than one bit because there's lots of exceptions that can happen. Was there a question in the? Good. That's a really good. You're thinking like a computer architect. So what happens if you throw an exception while you're in the exception? If the exception handler throws an exception, I think the answer there is, and Dan, you can correct me if I'm wrong. I think you write those exception handlers very carefully to make sure that can't happen. And there is a way to mask exceptions. So there's actually, because we're talking about control bits, you can actually temporarily tell the system to ignore these exception signals that are coming in. Okay, but you can't do that for too long, because if you do, you'll miss important things. Like the exception that, the disk drive is melting. You want to catch that one pretty quickly. So, but yeah, that's a great question, because, because you're in this funny position already, and then you get an exception in that code. What do you do? So basically, we're going to make sure that can't happen. Okay, so there's two kinds of exceptions. There are restartable exceptions where the exception happens and you can recover from it and then continue. Okay, so what's an example of that? Well, recoverable exceptions happen all the time. When you have a TLB miss, right, that's an exception that you can recover from. How do you recover from it? Well, you go fetch in the part of the page table that you need in the TLB. Same thing if you have a cache miss. How do you handle a cache miss? That's an exception that once the cache gets loaded, you go out and fetch the data from the next cache, right? Once you know that data is in the cache, you can go continue that instruction. So a restartable exception, basically, what happens is you've got a pipeline, and I'll show you an example of this in a second. You've got a pipeline, you flush the pipeline. Remember we did that when we talked about branching, right? And that if you mispredicted the branch, you would have to flush the pipeline so that because the instructions you thought were going to run, you actually weren't going to run. Well, it's the same thing here. You flush the pipeline. And then you execute the handler. And then once the handler has done its job, you can go back and go back to where you were and start running the instruction again. And so normally what you'll do is you'll flush even the current instruction, the one that was running at the time of the exception, and then you just restart it. Okay? And you have to make sure that everything works out okay. But in particular, as long as that instruction hasn't written any registers or memory, so if it was in the first 3 parts of the instruction pipeline, then you could just restart it. It won't have caused any problems. You just have to make sure that its registers haven't been messed up. Okay? So what you'll do is, the other little detail is that what gets saved in the exception program counter isn't, it's not the address of the instruction that caused the exception. It's actually that plus 4, because we've already incremented it at the time we're running that instruction. So you just have to, if you look in the book, it's just a minor detail, but if you look in the book, they show you kind of how the wires are all connected. So when you wake up, you have to, you realize that the PC you have in the EPC is actually 4 more than it should be. So you just have to deal with that. Okay, and the handler can deal with that pretty easily. Okay, so so exception happens, right? You get woken up. You flush the instructions. The transfer gets controlled to the special address where this handler code is. What does that do? Well, it reads the cause register, right? It looks at those bits and it says, okay, it was this type of exception. Either it's a restartable exception or it isn't. If it's restartable, it does what it has to do. So if it was a TLB fault, it initiates the request to read the page table into the TLB. And then, at some point, it's going to use it uses the EPC to return back to the program, right? So it handles the exception and then jumps back. And I'll show you an example of this in a second. If it's not a restartable exception, that means something bad happened, like an overflow or an opcode that was illegal. Then it just terminates the program and reports an error. Okay? So, when your system crashes and you get like segmentation fault, right, and it shows up on the screen, I'm sure you've all seen that by now, that's what's doing it, okay? Okay, so that's all great, except that, remember, we're trying to be so smart about running lots of things at the same time, right? We've got these pipelines that are running 5 stages at a time. We're doing out-of-order execution. We're speculating. We're predicting branches. We're doing all this crazy stuff, right? And it was hard enough when nobody was bothering us, right? When we just had a program and we were just trying to run it. Now all of a sudden we've got these events happening that we have very little or no control over when they happen. And how do you deal with that? So, think about an overflow exception. So here's an add command, okay, an add instruction. And, if that thing throws an exception, it'll happen in the execution stage, right? If it's going to overflow, it'll overflow in the execution stage. And so, you've got to be a little careful. You've got to make sure that this register 1 hasn't been, clobbered in any way. Okay, so you sort of have to stop it in its tracks, right? Because otherwise, this add instruction is going to write garbage into register 1, and it needs register 1 when you run it again. If you were going to run it again, it would need register 1. So, so basically, it does the flush. It sets the the cause and the EPC register, and then it jumps to the handler. Okay, and so the logic of this ends up being very much like a mispredicted branch. So here's the example. We've got an and, an or. We're doing an add, and then we're going down here. Let's say that when we're doing that add, we get an overflow exception. So right then and there, right, this exception happens. Store store overflow in the cause register. Store the PC of this instruction plus 4 into the exception program counter, and then transfer control to the handler. So what you'll do is you'll do kind of like what you would do when you mispredicted a branch. You would basically flush all these instructions. So you'd flush these 2 instructions plus the current one. Okay? And remember how we flush instructions? You set all the control bits to 0 so that nothing gets written anywhere, is basically. So the instructions still do stuff, but they don't have any noticeable impact. They don't change any registers. They don't write memory. Okay? So you do that. Then you transfer control over to the a new instruction, which is the first instruction of our handler. Okay? And then you run the handler does what it does, and then it returns control somewhere. Okay? And by the way, one thing the handler might do is go to sleep until it gets woken up. Okay, so it might not jump right back to the program immediately. Yeah? Who writes the handler? The handler is, I think the handler, that's a really good question. Is the handler, so the good news is you don't write the handler. And I don't believe I think it's part of the libraries that ship with the processor. So I think it'll just get included by the linker and loader. Is that what it comes with? Yeah, so it's the OS's library, but I don't even know if the OS implementers actually write that or if it's something that comes with the processor. There's probably some combination. Yeah. Yeah, so, processor will typically come with libraries. Okay, but there are some operating systems that actually do let you write some of your own handler routines. And for example, on a page fault, you might want to do something clever, like instead of going to your disk, you might want to go to the memory of another machine on the network. So there are operating systems that let you mess with those sorts of handlers. But in general, it's not something that a programmer has to worry about. It's at the operating system or below. Yeah. That's a good question too. So I think in general those are higher level than this. Okay, so these are for physical exceptions that are happening. Is that right? In a throw and a catch? Oh, the question is like for something like a throw and catch. Is that the same mechanism for that kind of exception handling? Or yeah. So okay. So yeah. So that's up. Typically, it's up in the. Yeah, so when you write your Java program, you sort of throw the exception. So it's actually the same. Yeah, it's kind of the same word, but a different meaning. So that's a good clarification. Any other questions about this? Yeah. I'm sorry? Yep. They can't throw. That's a good question. So when you when you flush these instructions, is it possible that they might still keep running and throw an exception? And I think that might actually, you do have to handle the case of multiple exceptions happening in the same pipeline. So I'll talk about that in a second. Whether the flushed instructions can throw exceptions, that's a good. Yeah, then the ALU could consumably, you could actually get another exception that way. And you have to be able to, your handler has to be smart enough to deal with that. Yeah.
What happens if, say, in that SLP, if that was something else, you got an exception at about the same time?
So the question is, what if, one of these other instructions that was running also got an exception? So we'll talk about that in a second, although I won't have a perfectly crystal clear answer for you, but you do have to handle that case. So let's handle it now. Okay, so as the last two questions have pointed out, an additional complication here is that we're not just running one instruction, we're running lots of instructions. In fact, in that architecture, we're running at least 5 instructions at a time. And because of that, it's quite possible that, in the same clock cycle, more than one instruction throws an exception. Okay, and the example here is that let's say that you have a load word that hits a page fault in the same, in one part of the pipeline, at the same time that you get an overflow exception in the execution part of the pipeline, right? So what do you do there? And so you have to be able to handle it. There's 2 methods for doing it. There's what's called precise exceptions, which is what most processors do. And basically, the approach here is to deal with the earliest exception, so figure out which of those exceptions happen first, and then throw away the other instructions. You're going to flush those anyway, so then you'll eventually restart them. And for something like a page fault, what will happen, like if you do that load word later, chances are you'll still get a page fault, but then you'll be able to handle it then. Okay, so a precise approach to dealing with multiple instructions is you figure out which is the earliest instruction that was running, you handle that one, you flush everything after it. Okay, and then if those subsequent instructions, you're going to rerun them later, so you'll be able to catch exceptions then if you need to. Okay, but remember we talked about a bunch of stuff that's hard to deal with, right? We talked about this multiple issue, right? That we do wide issue of instructions, so we've got that problem we have to deal with. Things complete in different orders, we have to deal with that. And so, this is a little hard to do, okay? So some people have proposed a different approach called imprecise exceptions, where basically you sort of, you basically stop the pipeline, you transfer control over to the handler, you save whatever state you could from the pipeline, and you say to the handler, okay, you figure it out. Okay, so I've got multiple exceptions here, you figure out how to handle them. And, obviously, this is going to make some things easier in the hardware, okay, but it's going to make your handler, now your handler has to handle all these different combinations of things that could go wrong at the same time, okay? So my understanding, and from reading the book, basically this idea of precise exceptions is what all systems support. And I'm not sure if any popular systems actually support this other notion of imprecise exceptions. The cost of doing the precise exceptions is you end up, restarting a bunch of instructions that you're pretty sure are going to end up ending up right back in the exception handler. So you're kind of churning a little bit more than you should. Okay, but it's just that otherwise your handler code gets more complicated, and as a couple of you guys pointed out, that's code that you want to be rock solid, right? You don't want you want it to be as simple as possible because it has to work, and it has to work, in situations that aren't optimal. Okay, so you want to try to keep your handler code as simple as possible. All right, so that's this idea of exceptions. Now, remember, the reason we're talking about this mostly is because, first of all, it was kind of an open issue we had talked about page faults and we had talked about, overflow and things like that. We never really said how the system handles it. luckily, a lot of the concepts we've already studied in terms of setting control bits to 0 in order to flush instructions, and how we deal with mispredicted branches, we sort of had most of the technology that we needed to deal with these exceptions. We just needed to add a little more hardware to do it. But what's the main reason we're talking about it? The main reason we're talking about it now is this idea of I/O interrupts. Okay, so remember, interrupts in our terminology are similar to exceptions in that they're unexpected events. They're not part of the main flow of the program, right? But in this case, they're asynchronous. So the exception happened. We get an overflow exception because we got to the ALU, we did our add, and the add overflowed, right? And so that was tied to that add instruction. But something like an I/O interrupt, like I said before, somebody pressing on a key of a keyboard, that's got nothing to do with any of the instructions that are currently running. So it's a little bit more challenging to deal with. Basically, you can't just take the state of the pipeline and say, oh, okay, I know what to do, right? Because I know I was in the middle of an add and I look in my cause register. And then you know how to unwind it. With an I/O interrupt, you sort of need more information, like what device is this and what's the operation it's trying to do and so on, okay? So I/O interrupts can happen sort of in the middle of any given instruction, but the good news is they're not going to get in the way of our existing instructions running, okay? Whereas something like a TLB miss will, right? Until you service that, you can't run that instruction, okay? But I/O interrupts, the reason you want to service them quickly is because you don't want to miss the event that's happening, okay? But it's not because one of your existing instructions needs to run. So what does that look like? So let's look at memory. All right, we've got our user program here. This is our handler, basically. It's called an ISR, or an interrupt service routine. And what'll happen is, so let's say you're chugging here, you're doing addition, you do a subtraction. All of a sudden, you get an I/O interrupt. Okay? So what do? Well, you save the PC. It's just like an exception in that case. You save the PC, and then you jump to the special location in memory, which is going to have the code for handling that interrupt. Okay? Now, I mentioned earlier, there's two ways of handling these kinds of exceptions, and especially for interrupts. There's the kind that we talked about already, which is you have one handler and you have a cause register, and then the handler looks in the cause register. The other thing you can do is what's called vectored interrupts. And a vectored interrupt has a different handler address for each device. So you'd have one place you jump to if you get an interrupt from your hard disk. You have another place that you jump to if you get an interrupt from your keyboard, and so on. Okay? So either one of those will work. It just depends how you do it. But at some point, you get to the handler. The handler says, oh, okay, this is an I/O operation from this device or with this device. So now I'm going to perform the transfer, okay, right, either data out to the device or data in from the device. Once I've done that, I then use the PC that I saved to go back to what I was doing before. So it really is an interrupt. It's right. You're in the middle of doing something, right? Somebody comes and knocks on your door and says, hey, you have to stop what you're doing. You answer their question, and then you go back to what you were doing before. That's exactly what this is, right? The actual servicing of the I/O didn't really have anything to do with the instructions that you were running at the time, but you had to handle that interrupt. You had to deal with the device. Yeah. Yeah, it's the same mechanism here. You'll have to flush these instructions so that you can run these instructions. Okay, and then restart them. Yeah.
If an I/O port can have multiple devices, say USB port having keyboard and mouse, they would require different types of interrupt instructions.
Right. So the question is, sometimes you can have multiple devices on the same port, and so how does that work? And, I think Dan said this in an earlier lecture, that one of the, key insights of computer design is that, most problems or all problems can be solved with a level of indirection. So same thing would happen here is if you had that kind of situation, you'd have a handler that knew that there could be multiple devices there, there'd have to be extra status information to tell that handler which device it was, and then it would have to run its own code. So there's always this ability to shift between who's responsible between the hardware and the software. In this case, it's a little bit more of the software. Yeah.
What if we are doing the interrupt processing and then like another device interrupt us?
Yep. So, right. So this is, again, this is kind of a similar question and a real important one because it happens. What if I'm in the middle of servicing, the disk interrupt when, the darn user goes and presses the keyboard? What do I do there? And again, the way that tends to work is you're allowed to mask interrupts for a very short period of time, deal with that interrupt, and then return control. So, and hopefully you do that before... You do that fast enough so that you don't miss that next interrupt. And you can actually, so you can queue the interrupts. Okay, okay. So, and where do you queue them? This is something the operating system would do? Right. Yeah, so, okay, so what Dan's saying is right. Yeah, but the key interrupt will be, so the question is, so what Dan's saying, and it's right, is that you have to be able to queue interrupts. The question is, though, there's this moment of vulnerability where you're handling one interrupt and you can't be interrupted doing that. And during that, you can mask interrupts. Now, what you need to do is, make sure that in the shortest amount of time possible, you do whatever bookkeeping you have to do so that you don't lose the interrupt. And so queuing it is definitely... but that's also something that's going to happen in the operating system, I believe. Yeah, okay, so the hardware is going to queue up the interrupts. Okay, so I will have to spend my Thanksgiving seeing if it's a hardware. But it's a real problem because you don't have control over these events happening. And the one control you do have is this ability to mask interrupts. But you can't overuse it because if you do, you would miss interrupts, and you can't miss interrupts. So, any other questions on this stuff? All right. Yeah, it's complicated. These are especially hard because they really are asynchronous, and so they're just coming in, and the processor's reacting to them. Okay. All right. So, but that's the basic idea. So, we talked about exception handling and. How you transfer control to a handler, deal with what you're doing, then go back to running the program. I/O is handled in a similar way, except that it's this kind of funny thing where the interrupt isn't related necessarily to the program that's running. It was caused by some external event, but you use basically the same mechanism to handle it. Okay? So, why is this a good thing? Well, so here's just an example. We looked at a similar example before. So imagine you had a hard disk that was active, say, 5% of the time. And let's say it costs you 500 clock cycles to service the disk interrupt. So remember, what's going to happen is this disk is going to, the way we're talking about it now is this disk is going to try to transfer a page in 16-byte chunks. So you're going to get interrupted for every 16-byte chunk of, say, a 4K page. Okay, so it's going to be a bunch of interrupts that happen. So the speed of the disk, let's say, is 16 megabytes a second. We're going to run it 5% of the time, and we're going to get an interrupt for every 16 bytes. So that ends up being about 50,000 interrupts a second. Okay? And again, this is obviously just an example. 50,000 interrupts a second, each one costs you 500 clock ticks. So that's about 25 million clock ticks a second. If you're running your processor at a gigahertz, or a billion instructions a second, that's about 2.5% of the processor, okay? So if you remember when we looked at it last time, we had a slightly different situation, but we were saying, if we had to check that disk all the time, if we're polling, it could take up to 40% of the processor. In this case, 2.5% is maybe possible. But the truth is, the way that disk I/O tends to happen is through something that I think Dan mentioned a couple lectures ago when we were talking about virtual memory, which is this idea of direct memory access. And direct memory access is, again, additional hardware that lets an I/O device transfer a big chunk of memory, a big chunk of data into a place in memory. And basically what will happen is it wakes up the processor once that entire transfer is done. So our CPU that's running, that pipeline with the multiple issue and all this stuff doesn't get interrupted for every 16 bytes. That's dealt with by a different sort of coprocessor in the system. And it gets woken up, our processor gets woken up when the transfer is completed. Okay, and that's called DMA, and that's really the way you deal with high-speed devices like disks and networks. Okay, so again, for a mouse, 30 times a second, you don't need to do this stuff. For a keyboard, there's even some of you are the fastest typers around. You're only typing, I don't know how many words a minute you type, but it's not, it's not a million. So that kind of stuff you can handle with interrupts or even with polling. High-speed devices, high-bandwidth devices, you're going to use DMA to do it. And still, this mechanism that we've come up with, this idea of interrupts, is the way we're going to make sure that the processor learns when something outside happens. So for example, if you're doing virtual memory, well, it doesn't even have to be virtual memory. Let's say you have a cache miss. That cache miss, it goes level 1, level 2, level 3. At some point, it has to go out to disk. Rather than, polling to see when that disk returns, you just go to sleep, some other process runs, and then you get woken up when that request from the disk has been brought into memory through DMA. Yeah. Yeah, I think, so why is it only 16 bytes per interrupt? Because remember, that's supposed to be coming through, some registers. If you remember how we did that, we had a data register and then we had a control register. And so the idea is you don't want those registers to be too big. Yeah, so the question is, why don't we just have one big interrupt that passes and everything? And that's exactly what DMA does. But you have to have almost a separate processor to handle that, because somebody has to keep talking to the disk to make sure the bytes are coming in, and putting them in the right place in memory. Well, you could stream data from the hard drive, but somebody with control over memory has to be there to take it off of the line and stuff it in the memory. Right? And you can either have your main processor do that, which is kind of what this is assuming, which is kind of a dumb thing to do if you're getting a lot of data, or you can have a separate piece of hardware that's doing that, that's basically handling that for you off to the side. So your main processor is doing what it normally does, and there's a little coprocessor that's doing nothing but, it's called a DMA controller, that's doing nothing but, bringing chunks of data from the outside world into memory and writing chunks of data from memory back to the outside world. And then you get an interrupt when it's done. So it is exactly what you're saying. This is a little, you wouldn't do this, okay, is basically the answer. It's because it's too slow. So it's a little bit, that's what you're saying, that doesn't make sense, and I'm sort of saying, yeah, you're right. It's just there kind of to show you why you need some other way to do it. But the important thing is DMA, it's still interrupt driven. It's the same mechanism we're talking about. It's just you're dealing with bigger chunks. Okay? All right. So that's all I wanted to say about I/O and interrupts. Let me start talking now, and maybe we'll get through it, maybe we won't. But I just wanted to quickly talk about one other kind of I/O device, which is the network. And basically, networks are the I/O device for the rest of the. That's how a computer talks to the rest of the world. And so this slide is really just talking about sort of the evolution of networking. Originally, the idea was I had this really expensive printer. I have 3 computers. I want them all to be able to share the printer. So that was some local area networking, then sharing files, then communicating across users, and now communicating across networks of computers. So the internet, as we know it, was actually invented quite a while ago, and there were some guys at DARPA, which is actually still around. It's the Department of Defense research agency, and they had this idea of an intergalactic network, right? That all the computers in the world could talk to each other. And in 1962, they built, in 1962, this was the internet, right? You could write it on the back of a napkin. It was 4 sites, UCLA, UC Santa Barbara, SRI, and Utah, okay, because these were the research places that were involved in this project. And that was the initial internet, was those 4 nodes. The internet has basically been growing exponentially since 1962, okay, which is why it's so ubiquitous now. A big breakthrough was in 1973 when Robert Kahn and Vint Cerf invented a protocol called TCP, which really enabled reliable communication between all these different computers. So I'll talk to you a little bit about TCP in a second, okay? But this is where it comes from, was really this idea that some people in UCLA wanted to be able to share files or send a message to somebody at SRI down the street, and this is sort of the start of that whole thing. So really amazing. I'm sorry to say this is actually within my lifetime that this started and has gotten to where it is today. It's really impressive, and really amazing to me, by the way, that in 1973 these guys invented this protocol that basically is still working, from a system that was maybe hundreds of nodes to the billions of devices that we have connected today. It's really amazing. Sometimes people get confused between the internet and the World Wide Web, right? The World Wide Web is a protocol that's built on top of TCP, and the World Wide Web, I'm sorry to tell you guys, was invented within your lifetime. And so, someday you'll be up here and you'll be having to admit that. The idea of the World Wide Web was that you wanted to be able to share documents with people. And Tim Berners-Lee was working at CERN, which is the big physics lab in Switzerland. They wanted to be able to share data with with colleagues around the world. And the World Wide Web was his idea of how you could make that easily happen, and it all had to do with hyperlinks that would link from one document to another. This is an interesting picture of the world's first web server. I thought you might find this interesting. It's probably a little hard to read. So there's a famous story that Tim Berners-Lee, when he proposed this the World Wide Web in a memo to his boss in March 1989, his boss read it and wrote this comment on it, which basically, if you can't read it, it says vague but exciting. Okay, which is really funny because, you probably spent a lot of your school career, turning in papers and getting professors writing obnoxious things on them, and you should never be discouraged. Now, this comment isn't so bad, right? Because he said it was vague, which is a little bit of an insult, especially if you're a scientist. But he did say it was exciting. So basically, and based on this paper, his boss gave him permission to work on this project. So I guess it was successful. But the reason I show this is because I know I'm guilty of writing nasty things on my students' papers sometimes. And just, if you don't let that stop you, okay? Because, things like this happen. So, okay, so that's the World Wide Web. So now what I want to do quickly is just sort of drill down a little bit into a little bit of the nuts and bolts, not too much. Obviously, we have whole classes on this stuff. So there's kind of 2 ways that networks work. There are shared networks where there's basically like one wire, and all the machines are on that wire, and you have to share the wire. So you have to split it, over time or over frequency, or you have to do collision detection and back off to make sure that things aren't interfering. So this is the way phone networks worked in the old days. There used to be this thing called party lines, where a single phone line would be shared, and this was before my time, would be shared across a bunch of houses, and you'd pick up the phone and listen to hear if anybody was talking on the phone. If they were, you'd put it back down, and you'd try later to try to use the line when it wasn't busy. What you really want to do, and the way the network works today, is what you really want is switched communication, right? Because the problem with this scheme, it's actually not, it's cheap in terms of hardware, but it's complicated because you have to do the coordination. And it's slow because your bandwidth is limited by that one wire. So the total bandwidth, the total amount of data that can be flowing through the system at any time is basically the amount of data you can put on that one wire. And so what you really want is a switched network where it's kind of a peer-to-peer thing where any node can talk to any other node with a single, a dedicated line, okay? And so what you end up having to do for that is you have to build one of these big switches that's basically, the way phones used to, worked once they went from that to this, where, there had to be an operator that said, okay, this phone wants to talk to that phone, and you patch in the right chords, and then there's a direct connection. So this is the way that this is the way that that switches work today, that networks largely work today, at least wired networks, because that way you get sort of the aggregate bandwidth of all these wires. So the amount of data that can be moving through the system at any time is kind of the sum of the data that can be on all these wires, as opposed to just on one wire before. Okay? So then what you do is you take a bunch of these switches and you get them to talk to each other. Okay? So if you want to take, the internet from being, those 4 nodes that they were in the beginning to being, 5 billion nodes or however many things are on the internet today, what you do is you have switches being able to talk to each other, and then what you need to be able to do is what's called routing, is that you need to be able to have, if you have a message here that needs to go to here or vice versa, you have to be able to send a message through this network of switches to the destination and then have the answer come back. Okay, and so these switches have to be able to talk to each other in order to move messages from one to the other. And so you need the ability to name destinations and sources, and you need the ability to, for each of these routers to sort of figure out, hey, I've got this message, I want to get it over to this machine over here. How do I do that? Who do I give it to next if I don't have a direct connection to that machine? And that's what's called routing. And if you ever wondered what companies like Cisco and Juniper and other companies like that do for a living, that's really what they do, is they build those boxes. And they're effectively very specialized computers. They have their own operating systems. They have custom processors that are built, optimized for being able to switch messages back and forth. And then they've got a lot of smart software in them to be able to do this routing efficiently through the network. Okay? All right. So, how do these messages work then? So let's say you had some data that you wanted to send. So this is a command, or, if you were talking to a disk that was, in another system somewhere else, maybe there's an address for data that you want to get, or maybe it's actually the data. So you have what's called the payload, which is the actual message that needs to get sent. And then you have stuff around it, like a header and a trailer, where the header says, who's sending the message, where does it need to go, so you need unique identifiers, right? So IP addresses are one example of identifiers that you'd see. So, the machine at this IP address wants to send this message to the machine at this IP address. Doesn't know how to get there, okay, but you give it to a router, and the router is going to figure it out. You have to say the length of the message, and then there's a couple other things that you need to add. So a checksum is a code that you create by, basically hashing the bits in the data. And so you want to make sure that when a message goes from one point to another, right, it's going to go through all these intermediate sites. You want to make sure it doesn't get garbled. And so when the message gets to where its destination, you can check, does the payload, when you run the algorithm on it, give you the right number for the checksum? If it does, that means with high probability that none of the bits got corrupted. If there's a mismatch there, that means your message got messed up, and you should ignore it, okay? And then the other thing you need to do in some protocols is you need to be able to acknowledge that you got a message. So in TCP, which is this guaranteed delivery protocol, a sender is going to keep sending the message out until it hears from the receiver that it got it, okay? And that all happens sort of at the protocol level. Yeah?
So the payload bits can get somehow messed up.
Yep. Yeah, I think so. I think any of the bits can get messed up.
Then how do they deal with not easy to get a message?
Yeah, so I don't know. So the checksum might actually be over all of that stuff. have to check on that. But that would be the way you do it. And then you'd check in the protocol before you return the message to any higher level programs. You'd have to catch it there. Yeah, one more question. Yeah.
Considering how much the internet is actually used,
Uh-huh.
I can see like millions and billions of places where the bits get corrupted, but the checksum still is pseudo correct. So what happens then?
So the question is, are there ways when bits could get messed up and the checksum would still come out okay? And the answer is that the algorithms that you use for doing this, you can get the probability of that happening to something very, 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 very small. It's not perfect, but for practical purposes, the chances of having a corrupted bit and the checksum still be correct is, and I don't know exactly what the numbers are, but trillions to 1 or something like that. So you can do the hashing, so it's that way. Okay, yeah. Yeah, if the destination of the source ID gets corrupted, again, you're going to have to detect that. And so I think that the checksum, I think you might have to do checksum on that stuff as well to make sure. Yeah. How can you not run out of IP addresses? Yeah. So the short answer is that we did run out of IP addresses. So all the IP addresses have been spoken for, and there's a new protocol called IPv6, which has expanded the... What's that? A lot of things are still using IPv4. It's going to shift because all those numbers have been allocated. They're not all currently in use, but they've all been spoken for, So it's going to change. All right, so what I want to do next time is I'll just bring this up a little bit. I want to talk a little bit more about redundancy, and then, next week's the last week of class, so we're going to try to just talk about a few more things you might find interesting. So have a good Thanksgiving break, and we'll see you next week.